So, whenever we have partial fractions and the denominator is quadratic, such partial fractions can be converted to three categories. That is, the quadratic denominator can either be factorized and converted to linear, for example, x minus 1 and x plus 1, or the partial fractions, if factorized, turn out to be perfect squares, like this. Or the quadratic denominators can neither be converted to linear nor are perfect squares, such as x squared plus 1. How do you simplify this, bro? So let's look into the first category. If any of you wants to write these down, so feel free to. So for the first example, uh, it's like how we always solve such questions. We start by simplifying the denominator. I'll apply this algebraic identity, which we studied back in middle school. A plus b, a minus b is equals to a square minus. So once I simplified this, I can rewrite this as a over x plus 1 plus b over x minus 1. And after cross multiplying, I will be left with a into x minus 1 plus b into x plus 1. And I cancel off the denominators simultaneously. Now I can either apply comparing coefficient or the Kawada method. I'll use the Kawada method since it's the easier of the two. I'll start by taking x as 1, so this cancels off. So I'll be left with 1 plus 1 b on the right hand side and 3 into 1 plus 1, yeah, on the left hand side. So I have 2b is equals to 4 and b turns out to be, so when x is equals to minus 1. So this cancels off. So I have minus 1 a and 3 minus 1 plus 1. So minus 2 on the left hand side and minus 2a on the right hand side. The minuses cancel off and I'll be left with a is equals to 1. I must leave my answer as a partial fraction. So it would be something like 1 over x plus 1 plus 2 over x minus 1. This would be the final answer. Now, for our second example, we have this. This cannot be simplified so easily, so I must try breaking the middle term, or just simply the quadratic formula. So let's try this by breaking the middle term. So I have x square minus 5x plus 6. I can write minus 5x. We have two numbers with the same signs. So minus 5x should be written as minus 2x minus 3x and plus 6 and x squared remain as they are. Taking x common would leave me with x minus 2 and taking minus 3 common would leave me with x minus 2 yet again. And thus the two factors turn out to be x minus 3 and x minus 2. And thus this fraction can be rewritten as 2x minus 1 or x minus 2 and x minus 2. It doesn't matter which order you like. The final answer should be the same. So a x minus 2 plus b x minus 3. So cross multiplying would give me x minus 3 a and b x minus 2 after I cancel off the denominator. So now I can simply apply the Kawada method. So when x is equals to 3, I have 0a and plus 3 minus 2b. And on the left hand side, I have 2 into 3 minus 1. So 5 is equals to b. B is equals to. I still have to find a. So to find a, let's take x as 2. So this can. So 2 into 2 minus 1 is equals to a 2 minus 3 minus a is equals to 3 and a turns out to be minus. And I'll leave my final answer as a fraction. It should look something like this. X minus. Just finally recheck if you substituted A and B correctly. Yes, I did. So this is my final answer. Now the second category. If the quadratic denominator is a perfect square, something like x plus 1 whole square, x minus 1 whole square, or and yeah, whatever. It should be a whole square, but so whenever I have a whole square, I must write a fraction twice using this. First without the whole square and the second time with the whole square. So I have a plus b. The first time I'll have x minus 1 in the denominator. The second time I'll have x minus 1 whole square in the denominator. And then finally I'll cover x plus 1. C over x plus 1. And also appreciate the fact that this should essentially be a cubic denominator, but we do have a quadratic part to it. And yeah, I'll simplify this by cross multiplying, and not just like I don't blindly cross multiply. I don't blindly cross multiply. In such a case where the denominators or fractions seem to be complex, compare the fraction with the original denominator. Like this fraction has x minus 1, but it lacks one x minus 1 and one x plus 1. So multiply this by this. In this case, this fraction has two x minus 1s and lacks x plus 1. So just multiply x plus 1 here. And in this case, this fraction has x plus 1 but does not have two x minus 1s. So multiply these two. And then after cross multiplying, we will be left with something like a into x minus 1 x plus 1 plus b into x plus 1 plus c into x minus 1 whole square, and yeah, the denominators cancel off simultaneously. Now let's start by taking x as 1. So this cancels out. So 1 plus 2 into 1 is equals to b 1 plus 1. So 2b is equals to 3 and b turns out to be 3 over 2. Then when x is equals to, let's take it to be minus 1. So 1 plus 2 into minus 1 is equals to c into minus 1 minus 1. So I have minus 2c and yeah, minus 1. So, or wait, this was a whole square. So I have c minus 2 whole square, and this turns out to be 4c. And c finally turns out to be minus 1 over 4. And finally, I'll be left to find a. when x is equals to, I cannot cancel anything off, so let's take it to be a simple number when x is equals to 0. So wait a second, I need more space. So when x is equals to 0, I'll write this thing as 1 plus 2 into 0 is equals to a 0 minus 1, 0 plus 1, and plus 3 over 2 substituting b. So, and finally I have to substitute c and 0 minus 1 whole square. Thus, after simplifying, I have something like 1 is equals to a plus 3 over 2 minus 1 over 4, and a turns out to be 1 over 4. And I, I'll have to leave my answer as a partial fraction. So this can be something like, just a second, and I have x minus 1 whole square, and x plus 1. This, my folks, is my final answer. And with this, we come to our last and final category. What if the quadratic denominator cannot be simplified? Like, it can neither be converted to linear nor is a perfect square, and is and should remain as it is. In such a case, in the numerator, we usually write a, but in this case we won't. We write this as ax. This is the rule. All mathemat- all mathematicians should stand by this rule. Alright. So, and finally we come to x minus 2. And this will be written as it is, since, yeah, it's linear. And with this, I have 3x plus 2 is equals to ax plus b into x minus 2 plus c into x square plus 1. Now, if even if I apply Cauchy method, this should like remain complex, and my instinct suggests that I should simplify this. Like, just leave it in this form for now. And yeah, 3x plus 2. First of all, how about I take x as 1, or rather 2. So this cancels off and this, and I'd be left to find c. So c, 2 square plus 1, and on this side I have 3 into 2 plus 2, and c turns out to be 8 over 5. And just make the working a bit smaller. I doubt space issues. And yeah, when x is equals to, let's take 0, so this one's fine. And yeah, I have something like 3 into 0 plus 2 is equals to 0a, or rather just 0, and minus 2b plus 8 over 5 and 0 square plus 1. So simplifying this would give me something like 2 minus 2b and plus 8 over 5. And then finally a. So I cannot cancel anything else off. So the thing I can do to help myself is just take x as 1 because it would be easier to simplify than other numbers like 20 and so on. Never take numbers blind. That's my advice. Substitute b, 1 square plus 1, and yeah, I'll end up with minus a, and minus 1 over 5 becomes plus 1 over 5, and 16 over. I have 5 here, and a turns out to be minus 8 over 5. I can write my final answer down as, just a second, minus 8 over 5x, and b was minus 1 over 5, and in the denominator I have x squared plus 1, and c I have as 16 over 5, and the denominator was x minus 2. And appreciate the fact I can further simplify. Take minus 1 common 2 and take 5 to the denominator. So I have something like this. This is my final answer. So these are the three categories which you can encounter. The first one is the simplest. The second one just required you to know that whenever you have perfect square, you will have to write it twice like this. And if you have something which cannot be simplified, which is quadratic, you will have to write it like this. And to make simplification easier, just expand this. The rest remains the same.